Okay, next up, question 3, it says, in statistics, the standard normal distribution, phi, is central to the theory of sampling. This distribution, often referred to as the bell curve, is defined as follows. Okay, phi of x is equal to 1 over the square root of 2 pi times e to the negative x squared over 2. Okay, so here's a graph of the normal distribution, and given its bell-like shape, people often refer to this as the bell curve, as I mentioned here in the problem. Okay, now in statistics, this is known as a probability distribution. Okay, it's describing how this variable x is, well, distributed. Okay, so for example, let's say x denotes SAT scores across the country. Now, it turns out that scores on a standardized test, such as the SAT, are usually normally distributed, meaning that their distribution has this bell curve shape. Okay, now this curve is normalized, so the mean score is here at 0. And so scores to the right of 0 indicate scores above the mean, and scores to the left of 0 indicate scores below the mean. And so we can see here that most students score at and around the mean. And then as the score increases, okay, the number of students achieving that score tapers off, with very, very few students earning a perfect or near perfect score, and likewise, very, very few students earning a score that's significantly below the mean. All right, now I know this is not a statistics class, so if you have not seen anything like this before, don't worry. But if you have, then this is a good connection to make to all the stuff we're talking about on series. Okay, so in any event, let's jump into part A. It says, find the Maclaurin series for this function. Write your answer using sigma notation and in expanded form, and state the interval of convergence. All right, so to begin, let's take the Maclaurin series for e to the x and replace x with negative x squared over 2. Okay, so here's phi of x. It's 1 over the root of 2 pi times e to the negative x squared over 2. And so I'm going to trade in this exponential term for this series, where instead of x to the n, I now have negative x squared over 2 to the n. And note that since the Maclaurin series for e to the x converges to e to the x for all x, okay, making this replacement won't affect that convergence, and so this series converges to phi of x for all x as well. All right, so now let's go ahead and rewrite this expression that we're summing. Okay, so I have a negative 1 to the n here, and x to the 2n here, and then a 2 to the n. I'll put that in the denominator, and I still have the n factorial there. Okay, now let's go ahead and expand this series. So when n is 0, I get negative 1 to the 0, that's 1, times x to the 0, that's 1, divided by 2 to the 0, that's 1, and then 0 factorial, that's 1. So when n is 0, I get this term 1. When n is 1, we get minus x squared over 2 times 1 factorial. That's right here. When n is 2, we get plus x to the 4th over 2 squared times 2 factorial. That's right here. And then a negative x to the 6th over 2 cubed times 3 factorial, so on and so forth. All right, so in conclusion here, right, we have the Maclaurin series for phi of x written in sigma notation, and here it is in expanded form, and the interval of convergence is from negative infinity to infinity. All right, cool. So now let's go on to part B. So part B says, use your series to approximate the integral of phi of x from 0 to 1 with an error of magnitude less than 10 to the negative 5th. All right, so looking at this graph here, we're looking to approximate this area in purple below the bell curve and above the x-axis as x varies from 0 to 1. All right, so integrating phi of x, well, I can pull out the 1 over the root of 2 pi. So we need to compute the integral then of e to the negative x squared over 2. Okay, now as an aside here, now we're going to approximate this integral using series, but you just as well may wonder, why can't I just use a Calc 2 technique, right, to find the value of this integral? Well, it turns out, and this is by no means obvious at all, and it's actually really hard to prove, but it turns out that it's not possible to compute the antiderivative of this function e to the negative x squared over 2 in terms of what are known as elementary functions. Okay, so in other words, I can't write down an antiderivative to this function in terms of polynomials, rational functions, trig functions, and the inverses of these functions. So things like logarithms or inverse trig functions, okay, just can't do it. Okay, so put another way, any integration technique that you've learned will not work, okay? And it's even worse than that. You might just say, oh, well, maybe it's just a really hard integral, and even though I haven't learned the technique, maybe there is a technique out there that would lead to an antiderivative in terms of these familiar functions. Well, again, there's this advanced result that says, nope, you actually just can't do it. No such method exists, right? So that's a huge roadblock, okay, to computing this integral. But as we can see, right, this function phi of x is really, really important in statistics, all right? People want to know the value of this integral, okay? And so that's where our series approach is going to come into play, all right? So to start, let's go ahead and trade in e to the negative x squared over 2 for its Maclaurin series, okay? And this is just the series we derived in part A. And now what we can do is integrate this series term by term. So we're going to get an x minus x cubed over 3, and then we still have the 2 times 1 factorial, and then we have a x to the 5th over 5, and then we still have our 2 squared times 2 factorial, and then we have a x to the 7th over 7, we still have the 2 cubed times 3 factorial, so on and so forth. Okay, now we need to evaluate this series at 1 and at 0, and then take the difference. Okay, now when I plug in 1, I'm going to get 1 minus 1 over 3 times 2 times 1 factorial plus 1 over 5 times 2 squared times 2 factorial minus 1 over 7 times 2 cubed times 3 factorial, so on and so forth. Note when you plug in 0, all of these terms go to 0. So in fact, this series is the result of this evaluation. All right, so we're getting there. All right, so what I want to do now is make a little space, okay, and next observe the following fact, right? This series that we're looking at, right, which gives us the value of this integral, is an alternating series. Okay, now I'm labeled this b0 minus b1 plus b2 minus b3, so on and so forth, where here it's understood that this 1 over the root of 2 pi has been distributed. So I'm saying here that this is an alternating series with b sub n equal to 1 over the root of 2 pi. And now for this first factor, I have, well, 1, 3, 5, 7, 9, and so on, right? So I have the positive odd integers, so 2n plus 1. And note here that I'm starting n at 0. Okay, now for the second factor, well, I have 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the fourth, and so on. So that's a 2 to the n. And then for the third factor, 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, and so on. So that's n factorial. All right, cool. So now we note that this sequence, b sub n, well, it's clearly decreasing, right? Because the denominator is growing to infinity, and the numerator is constant. So it's a decreasing sequence. So this first condition in the alternating series test is satisfied. And b sub n is also clearly approaching 0 because the denominator is approaching infinity, the numerator is constant. So the second condition in the alternating series test is satisfied. And so this is a convergent alternating series. Okay? And furthermore, right, since I know this series gives me the value of this integral, okay, I can go ahead and state an upper bound on the error in my approximation using the alternating series estimation theorem. Okay, so let's recall what it says. It says that the exact value of the series, which is s, minus our approximation, s sub n, and that's where we sum up until we get to the b sub n term. Okay, so this error right here in absolute value is bounded above by b sub n plus 1. Or put another way, it's bounded above by the first discarded term. Okay, so now what we're going to do here is we're going to go ahead and find the value of n, right, to ensure that our error is less than 10 to the negative fifth. Okay, so in this table I put up here, okay, so for these various values of n, I'm looking at the value of b sub n plus 1, right? This is the upper bound I'm getting on my error from this estimation theorem, right? Now for b sub n plus 1, I have 1 over the root of 2 pi, and now, right, I want to replace n with n plus 1 in this expression for b sub n. So when I replace n with n plus 1 here, I have 2 times n plus 1 plus 1. That's 2n plus 3. So that goes in right there. Then I have a 2 to the n plus 1 here. And then I have an n plus 1 factorial. All right, so now for these values of n, okay, I'm getting these values for b sub n plus 1. And I can see that when n is 4, okay, my error falls below this threshold of 10 to the negative fifth. Okay, so what does that say? It says that if I want to approximate this integral and ensure that the error is less than 10 to the negative fifth, okay, I want to go up to the b sub 4 term. Okay, so I'm saying that this series, which gives me the exact value of this integral, is approximately equal to this finite sum, where I'm going up to b sub 4, which is 1 over 9 times 2 to the 4th times 4 factorial. And then I just use a calculator here. I get a value that's about 0.341353563,817. All right, so there we go. And right, the alternating series estimation theorem, it guarantees, right, that this number, right, is within 10 to the negative fifth of the exact value of this integral. Okay, so now last thing I want to note here, so if you were taking statistics, okay, you might use maybe a website like this, right, that computes areas under the normal distribution. You also might just use a graphing calculator, but here I want to find the area, right, below the normal distribution and above the x-axis from 0 to 1, and so I'm looking for this area between 0 and 1, okay, and it spits out this area to be about 0.3413, okay, which is, of course, very close to what we have. It's within 10 to the negative fifth of what we have, in fact. Now, if you go to something like Wolfram Alpha, okay, and you type in this integral, okay, so one comment there, the exp, that's just the way Wolfram Alpha writes e to the negative x squared over 2. Okay, so it's called the exponential function. Okay, so notice it doesn't spit out an antiderivative. It spits out this ERF thing. Okay, this is a special function called the error function. Okay, but in any event, the approximate value it's spitting out is 0.341345, blah, blah, blah. Again, this number is within 10 to the negative fifth of our approximation. All right, well, that's a great place to stop. I will see you in the next video. Thanks.